Hey everybody, it's Ripley back again. Oh, we get to start using our integrals now. Think about it. We've been doing all this work with integrals, right? How to do them, how to take them, all that good stuff. Now let's start using them. All right, now let's keep this real simple. I'm going to keep it super simple. We know that the area under a curve, f of x on a closed interval from a, that's a terrible line, to b is easy, right? It's just the integral from a to b of f of x. I don't know where f of a came from. Sorry, must be after lunch. Getting a little food coma action going on here. Is the integral from a to b of f of x dx, right? And that's easy. However, what would happen, now let's think about this. What would happen if I threw another function in here? Let's say that this were, for instance, g of x. And instead of finding the area under the curve f of x, right, that was this guy, what if I wanted to figure out the area between the curves? That would be this guy in here, right? Now, I'm going to build this out. We're actually going to do this, and I'm going to introduce some new ideas to you. Okay? Now, how did we find the area under a curve in the first place? What did we do? We built rectangles, didn't we? And we added up an infinite number of infinitely thin rectangles of width dx, right? The width of our subinterval. So we are going to do exactly the same thing. Here's what I'm going to do. I'm going to build a rectangle. From this point hence, I'm going to call this rectangle my action. This is where the action is taking place. I'm going to build a rectangle right there, and then I'm going to build another rectangle here, and I'm going to build another rectangle here, etc., etc. But what we're going to do is we're going to let, excuse me, we're going to let the number of those rectangles go to infinity. We're going to let the width of the rectangles get infinitely small. Now I'm only going to do this once because you guys are going to hate me if I do it too many times because we've already done it a bunch. Let's think about what the height of this rectangle is. How tall is this rectangle right here? Well, do you agree that it would be f of x, the bigger of the two rectangles? Now, careful, it's not f of x, it's f of, let's call this point right here, I don't know, x sub I. It's going to be f of x sub I minus g of x sub I, isn't it? And then what's the thickness? Well, it's the thickness, which is commonly referred to as delta x, or the width of our subinterval, correct? Now, if I want to figure out the area of this thing, what would I do? I would let the sum, as I goes from 1 to infinity, of f of x sub I minus g of x sub I, that's the height of our rectangle. The width of our rectangle is simply delta x, right? Now careful, that's not the exact area, is it? That's the approximate area. Remember this when we first started putzing around with integrals? Well, as you can probably see, if I want the actual area, it's easy. I just let the number of these rectangles go to infinity, let delta x get infinitely small, and I would take the limit as n goes to infinity of the sum as I goes from, whoa, where did I get from 1 to infinity? Get rid of that. I'm sorry, you guys. As I goes from 1 to n, I'm fixing n as the number of rectangles that I'm going to take. I apologize. I would take the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I minus g of x sub I times delta x. Remember what delta x is? Delta x is always equal to b minus a over n. And what do we know that this equals? We've done this already. This is simply the integral from a to b of f of x minus g of x dx. Now, this is the formal theoretical way to build this, all right? But let me show you sort of a little more user-friendly way to think about it. Watch what happens. So let's take the same function. So here comes f of x, and then here comes g of x, and what did I have? I had g of x out here doing something like that, right? Let's just get close enough for government work. So here's a, and here's b. Now really what I'm doing, if you think about it, if I look at this solution over here, the integral from a to b of f of x minus g of x dx. Well, do we remember that the limit of a sum is the sum of the limits, and since integrals are built based on limits, I know that the integral of a sum from a to b of f of x dx is equal to the sum of the integrals. I'm subtracting, so, but subtracting is the same as adding. We just use negative integers, right? From a to b of g of x dx, right? Now, let's see what happens. I'll watch my colors here. The integral from a to b of f of x is simply all of this area under here, right? The integral from a to b of g of x is equal to all of this area. I suppose I should have labeled g of x. All of this area right here. So if you think of it as subtracting out area, I have a big area, which is the blue stuff. I subtract out the little area, which is the green stuff, and what I'm left with is the area in between. Now, that may be incredibly intuitive to you, and hopefully it is. All right, what we just found was all of that area. But what I really want to emphasize is I want you to start thinking about action. Let me make it in an obnoxious color. Action. You're actually going to build, no pun intended, a rectangle, and you're going to think of that as where the action is taking place. So it's always a good idea when you're doing these kinds of problems to figure out where that action is taking place. It'll make your lives simpler. So, I don't know, let's do a problem. Let's do a few problems. I'll do a couple of examples with you. I have to get away from this orange color or I'm going to lose my mind. All right, let's say that I want to figure out the area of the region. Now, you got to watch out. In your book, the region is, he'll call this R, this little script R, the area of the region bounded by, let's make it interesting. How about I'm gonna bound it, but I want it to be fun. Let's do the y-axis. Hopefully in your brain you're already thinking parenthetically x equals 0. Let's do y equals x squared minus 1 and y equals x. All right? So we're going to find the area of the region bounded by this. Now, the hard part about this is you're going to have to visualize this. If you do this without visualization, you're not going to know where the action's taking place. All right? So all I'm going to do is I'm going to try and do a quick sketch of this. So do me a favor. Before I do a quick sketch of it, you try and do a quick sketch of it. Now remember, bounded means cut off. You're containing this. So if we don't contain it, we've got an infinite number of area, or a potentially infinite number of area. All right, so give it a try, and I'll meet you back here. Okay, so let's see how you did. Well, first and foremost, let's pick the low-hanging fruit, as it were. Let's do y equals x, right? So there's that guy. And then I'm going to do y equals x squared minus 1. Well, what's that guy look like? That's a parabola, right? So I'm going to do it minus 1, and I'm going to go up here. And then, now this is where I got to be a little careful. I got the y-axis. So the y-axis is actually bounding this area right here. What the area that I'm talking about is right there. Okay? Now, the question becomes, where is the action taking place from and to? Well, I'm going to give myself a little sliver of action. This theme of action is going to come back again and again and again. So if you don't like it, tough. You're going to have to deal with it. The action is defined as where I am drawing rectangles from and to. Now ask yourself, which function is bigger on this interval? Well, I need to know what the interval is first, right? I'm definitely building rectangles from 0, from x equals 0, but I need to know what point this is. How do I solve for that point? It's easy. I set these two equal to each other, right? So I go x squared minus 1 equals x. I'm going to go x squared minus x minus 1 equals 0. You agree with that? And nothing to it. Okay, well, how am I going to figure that? That's going to be ugly as heck, but we're not afraid because remember, we cannot, even though I'm going to end up with an ugly number here, I can always plug it into my calculator. But what we're really focusing on here is being able to set up these integrals, right? Okay, so maybe I should have done this as x. Ooh, just because I'm feeling a little lazy this afternoon, I'm gonna turn this into x squared minus 2. You see why I'm turning it into x squared minus 2? It's still going to be the same. In fact, I drew it more like x squared minus 2, didn't I? So this guy right here is y equals x squared minus 2. And then this gives me, Mr. Lazy Man, this gives me x squared minus x minus 2, right? Oh, now it's factorable. Thank goodness. That's what happens when you just pull one out of your ear, right? So this equals 0. So I get x equals what? -1 and 2. Now, what's this -1 thingy dingy? Oh, that's that point right there, isn't it? That's -1, excuse me, comma -1. But I don't care about that one. I care about this guy right here. So let's plug it in. I know that y of 2 had better equal 2. You agree with that? I'm going to have 2, comma 2. Now, remember, when I build this integral, when I find the area, I am taking the limits on x. I worry about where I'm drawing my action from and to, but that from and to part are limits on x, because I'm talking about delta x here, right? So where am I integrating from and to? Well, that's easy, right? From 0 to 2. Which function is bigger on the interval? Well, when you look at the graph, it's easy to tell that y equals x is larger than x squared minus 2 on the interval from 0 to 2. But let's say that we needed a check. I'm just doing a little scratch work over here, so I'll try and hide this. Let's pick a value between 0 and 2 and plug it into both functions and see which is bigger. Well, the obvious one is, let's look at x equals 1. Well, when x equals 1, I know I'm going to have 1 squared minus 2, which is -1, and I'm going to have just 1, right? So this guy is for x squared minus 2, and this guy is for x. So he wins. He's bigger. That's really useful. I often have students say, well, Ripley, how do I know that they don't change at some point? In other words, we picked 1, but what happens if these guys flip-flop in between 0 and 1 or between 1 and 2? Well, then I would have gotten one more solution out of this, wouldn't I? Clever. So all I got to do is take the larger function, which in this case happens to be x, and subtract the smaller function, which happens to be x squared minus 2. Slap a dx on there, and that is my area. That's pretty cool, huh? Nothing to it. All right, now if I wanted to clean it up, which of course you may want to clean this up, especially if you're having to do these by hand or on a non-calculator portion of a test, you'd go 0 to 2, and I'd go -x squared plus x plus 2. That's right, isn't it? dx. And it's easy. Nothing to it. This idea of action is really, really important. Okay? All right. Let's see. Let's try another one of these real quick.